Recording started. Hello everyone, my name is Kyun Kim. Today I'm going to talk about the engineering safer oceans and by bridging the structural mechanics and intelligent monitoring techniques. So I am working with the Department of the Navy Architecture and Ocean Engineering at Seoul National University. So let's get it started. So this is the overall picture of my presentation. So I will briefly introduce about our research group, Ocean and Shore Technology, and the section two is the main topic. So in total, I have six individual topics, but I will briefly introduce by showing the figure and video clips and the conclusions. So OST. So before that, let me briefly introduce myself. My name is Dogyun Kim again, and you can simply call me DK. So I was working with before I joining the SNU, I was working with the Newcastle University and the Petronas University of Technology. So my background is quite simple and clear. My father was also working with the Lloyd Register, and my supervisor uh, in the field of structural engineering, was working with the Busan National University for more than 35 years. And after that, he moved to the UK, the UCL London. So I will skip on that. And this is our research group named by the OST and two postdoc and many other postgraduate students. In total, we have around 15 students. Of course, we are willing to produce the young, talented researchers by providing the creative ideas. And before I joining the SNU, I was working with overseas countries for more than 8 years, so that most of the collaborators are staying in overseas. And yeah, main topic, bridging the structural mechanics and the intelligent monitoring. So since 2014, I have established OST. At that time, the name was the Ocean and Ship Technology. And now we slightly changed the name. So we target the ocean and the shore can be split into three, offshore, onshore, and the nearshore structures and the techniques. So basically, we would like to, focusing on the digital structural intelligence, digital, techniques, and we split into six individual research topics. So mainly, I was focusing on the limit state design, including the ultimate limit, fatigue limit, and the accidental limit, and the serviceability limit and the risk assessment. And since I come back to Korea, I am focusing on the structural sensing and the monitoring. This is one of the important topic for the digital, intelligence. And one more thing is the material and the structural integrity matters. Material failure, fatigue, and the fracture is pretty much important for us, especially for the development of the new, materials. And followed by the shore systems, including the offshore, nearshore, and onshore systems, especially for the line dynamics. So mooring line, the riser, and the chain, everything's pretty much important. And fabrication and the welding methods are one of the topic as well. And we focus very much focusing on the structure side, but at the same time, fluid structure interaction will be the main topic. So it's just like the paradigm shifting, and of course, we traditionally the approach by the physics governing equations and the resource intensive approaches. So process was the isolated domain analysis and the high fidelity simulations required, but it was quite slow. The higher computational cost required and conservative rule-based design is nowadays adopted. It's just like the allowable stress design and walking stress design. But at the same time, we can target our, future AI-driven, the vision and the future directions. It's just like the intelligent mechanics, the real-time insight might be required. So the process is going to be data and physics informed learning or the training and the multi-physics surrogated modeling is required. And all the time, every single moment we can, measure it from the sensor, and the integrated real-time monitoring system could be established, and the design can be optimized as well. So I will introduce five or six simple examples. The first one is the limit state-based structural safety assessment, and this is related to the ultimate strength. So as you could see here, that there are so many, accident still happened, especially it could be split into two, the vessels or the ship structures. Mhm. And still we need for direct safety margin evaluations, but the gap is also there, the over uh, reliance on the idealized assumptions in historical studies, historical data set, and the oversimplification of the complex variables in real-world shipbuilding. So we think that we would like to involve the ultimate limit state models into the high fidelity digital twins. Of course, it might take some time and the techniques should be improved as well. So we want to reflect actual as built or the as is condition for the life cycle assessment. So let's take a look at our research objectives. We want to develop advanced ultimate limit state or the limit state assessment formulas, like the design formula, empirical formula, so that we can see that the simplified unstiffened panel carved out of flat, and the stiffened panel, the hopper, or the many other shapes, wind turbines, and the hull girders. So nonlinear structural mechanics adopted and analysis, and by including the welding and etc. And the Scott will be the mathematical formula, AI-based algorithm development, and the GUI for the working with the major shipyard. So this is one simple examples for the carved plate. Recently, we investigated URS assessment framework development, and we were targeted minimizing the numerical simulation result, and the gap between the numerical simulation and the predicted values. And of course, applicability might be important as well. So the hull girder we split into the hold model and the stiffen panel and the plate. And also we adopted for more than 200, 2008, 2800 validated nonlinear finite element model cases. And we established our own, the design formulas. And also we checked the boundary effect. And also the welding is one of the important phenomenon for especially the shipyard, the shipbuilding, the engineers. So we also develop our own, the welding residual stress distribution, the equations, and the prediction techniques. And of course, this is the ongoing work and the future work. So physics embedded learning might be important for us. So the thermal and mechanical governing equation into the artificial intelligence loss functions. And we want to develop the surrogated model, and the comparative validation has been done. At the same time, the future work, we are also working on the AI agent development, the ontology matters, and original data set, how we could be able to handle all those things, environment and then the subject and the actions. So we will explore design, generatively, and optimize the multi-object trade-off. So that is just like the optimization methods. So this is, publication and the award, the history. The second one is the sensing and the monitoring. So we call the real-time structural health monitoring. And yeah, still we need for the realistic structural assessment. And the gap is conventional structural health monitoring is just like 5 or 30 minutes. The gap is there. And the direction is real time, how we could be able to, measure the real time structural safety by adopting the digital twin techniques. So the target is quite simple, ship structure and offshore and many others. So we developed our own, we called it conversion model, and for the real-time whole response reconstruction framework. Um, and also it is always challenging to measure, to, put the sensors for more than 100 or the 1,000 in the real ship. So which means that we have the limited measurement data set, and we established the conversion model. So how we could be able to utilize this limited number of the sensor, and how we put the select the location of the sensor and the mode, and replacing the repeated the numerical simulations. So of course the measurement reliability also the key issues. So three, so the PCA, the first most determination, we are aware that this is pretty much important for us. And also the Bayesian optimization for mode selection technique is adopted, and the stress RAO based determination technique. So all those things are, combined together. And we checked the, accuracy. It was not perfect, but much better than before. And in the future, of course, this is another example for the plate. So normally it is hard to, measure the real-time displacement and the corrosion or the material failure, something like that. So especially in the, the offshore field or the MRO, the business field. So we are also working on the vision-based sensing using the drone, and apply the physics informed the AI model, and the field measurement data integration might be needed. And this is one of the example. So we will extract the data from the real field. At the same time, we want to evaluate our structural, the conditions by extracting the von Mises stress view, and the shear stress and the XYG displacement or the strain energy, everything. We can visualize it and train it. For example, the CNN technique, something like that. And the FNO based framework is actually developed now. So this is the publication record, and it might take some time to be, publish additional, papers. And the material part, we are here, and the fatigue and the fracture is always the, big topic. So we can see that always the material fracture, small cracks occurred for the SML or the many other, structures. So normally we follow the ECA, the British Standard 7910, and the need is here. We need for realistic fatigue and the fracture assessment. But the thing is, the fatigue and the fracture is governed by the multi-physics degradation, the aging issues, and the flow size and the fracture. That must be, explicitly considered. So there might be the gap, and the uniform damage assumption is not always sufficient, and the large-scale hydroelastic and the flow-dependent effect might be difficult to be captured. So future way is also the combining with the AI technique. So yeah, tomorrow I will move down to the, the government office to present the liquefied the CO2, the IMO Type C tank, the development and the heat treatment techniques. At the same time, I would like to very much appreciate the great support from the Lloyd Register Foundation for my work. And we equipped the fatigue crack growth, the testing facilities, and corrosion is also one of my, the research topic. So we equipped the, the experimental, the the facilities, and we obtained the data set. And the physical model we established. This is the just like the physics, and the AI physics informed the neural network we developed by our own. And the future work might be because still have the limited number of the data set. So how we could be able to interpolate or the export, predict the future the data set. And this is related to the corrosion side. Nowadays, the Bayes corrosion depth analysis is one of the popular the technique. So based on the physically measured the corrosion data, and we would like to establish the future we call the time-dependent corrosion wastage model, so that we can combine with the structural part and the material, the corrosion and the crack, and the the core message is the artificial intelligence may provide an effective framework for integrating the physics model when addressing the problem involving the decrypted data, discrete data. So this is one of the applications, and this is the biolobate type, IMOC type tank for the liquefied the CO2 or the ammonia and liquefied the hydrogen as well. So example of the ECA, engineering critical assessment, and this is the ongoing work by application of the AI techniques, and especially for the HARS, the hit affected zone and the many others. The crack propagation simulation take a very long time simulations and publication record. And this is the line dynamics. So I'm also working on the mooring or the riser, and it is connected with the chain. And the people may think that the chain is mainly covering the tension, but at the same time it is subjected to the OBP and the I OPB and the IPB, the out of plane and in plane, the bending matters. So all the loads are subjected to the mooring chain, which means that the combined load shall be considered. And the fatigue should also be considered clearly. At the same time, the limit state are important, subjected to the repeated load. So progressive plastic deformation should also be, focused as well. At the same time, this is the global the analysis by using the Okaflex. We can see that the global motion is potent, global mooring system response, and the local chain. All those things shall be integrated as well. So we last 2, 3 years we investigated on the chain methods, and this is the brief procedure, and we would like to produce the safety evaluation diagrams. So every single analysis and we conducted by the nonlinear finite element analysis, and the displacement and the load type can be selected like the pure tension and the IBP tension and the OBP, and to combine all those things, and we try to extract the maximum values, and then we establish this kind of the diagrams. So from the Okaflex or the real-time, the simulation data set, and we extract the tension and the bending, the capacity, and then we can plot it, and then we can measure the safety. This is just like the real-time safety assessment. And also the material side, the repeated load uh, uh, may degrade the material side. So cyclic softening should also be considered, and the yield function. This is the existing models, and we try to combine all those things in the local analysis. So plastic response, we have the elastic shakedown, plastic shakedown, and the ratchet behavior. So we are now establishing this kind of diagram as well. So in the future, AI agent development is going to be, focused. We are now ultimate strengths established and cyclic behavior here. So we are now working on the surrogate model by developing the AI agent and the dynamic analysis, the AI development and the energy and the electricity, the cable line is also important. So this is the publications. And Yeah, we don't have enough time, so I will move faster. So shift forming is also one of the topic, especially this comes from the GTT, and they have their own, copyright. So we are willing to follow up how to form the first barrier. The thickness is just like 1.2 millimeter, but still you can see here we have the residual stresses and the thinning effect. So for the structural analysis, from the pressure, like the sloshing and the actual compression, shear, whatever it is, we want to investigate more, detailed, structural behavior. So this is the procedure, and we want to, follow up the, punching and the black holder, worksheet, and the die, using the LS Dyna. We are now working on that and simulation outcome, a very simple one. And we, found out that the manufacturing history shall be incorporated into the subsequent structural analysis. So this comes from the other research outcomes, and the AI application will also be focused as well. And the last one is the AI-based hydroelasticity. And as you can see here, very, very large floating structures. That demand is also the, rapidly increasing. And integrity, assessment is also required. So, yeah, hydroelastic effect and data driven framework is needed, and computational report efficiency might be the issue. So we developed discretized the model-based the message, uh, collaborated with the Texas A&M and the Florida Tech, the United States, and the physical data generation using this method, and we adopt the artificial neural network for the machine learning implementation. And at the same time, we want to see the fatigue life calculation and the validation as well. So this is the framework the, for the ANN, and it will be presented soon in Tokyo OMA conference. And this is one of the examples. Yeah, multi-objectives, the optimization methods, and the connector stiffness methods important, and the mooring structure interaction framework is also needed. So there are still many things to do. These are the twin applications. So this is the almost last slide. And I elaborated more than six individual topic. We have limited time. Please bear with me. And the summary might be here. We want to very much focusing on the digital structural intelligence we named DSI. And that is our core direction for advancing the structural safety, integrity, and the decision making by providing the AI agent system for the ocean and shore, infrastructures, and the physics-based mechanism, mechanics, and the conventional, the engineering method. They remain essential. Of course, it is very much important as the foundation of the reliable interpretation, verification, validation, and the design assessment. And the way forward is to bridging the mechanics and the intelligence modeling, the monitoring. So we would like to integrating the real-time sensing data. Of course, the noise and everything should be, adjusted with the physics informed and the data driven the framework. So that was my presentation. Thank you very much for your kind attention.